Welcome to the Physics 2 How-To video series, video number 2, where we're going to cover basic objects and coordinate systems. So again, we're going to cover the general coordinate systems that are used in the Physics 2 software, and then we're going to introduce each of the different types of objects and their parameters and how they work. Okay, and again, for those people that are watching this brand new, Physics 2 is a simulation tool that uses the new Electromagnetism V5 field models to compute forces and voltages between wires, magnets, and charges. And it is validated with experimental results. This validation can be seen in the new Electromagnetism series. There's a little quick demonstration in the introduction video to this video series. Okay, so where we left off in the last video, we learned how to put an object in the universe, change its shape, yada, yada, yada. Okay, and changed the code a little bit from last time. This is one of the improvements. Before we had this My Universe Clear that you did at the top. And what I've done, I've replaced that with a general purpose call called Clear All, which will also turn off the timer because we need the timer if we're doing simulations. It's a good thing to turn that thing off before you replace the universe or clear the universe. So I wrote that into a nice little compact function, so that's the first thing you call. Also, I updated some of the names, like we're calling these construction parameters, and over here we have function calls that need to be called in order to advance the parameters. We're going to explain that in a moment. Just to let you know, we changed the names of these variables based on what was being done for the astronomy software, because what we called them before was a little bit more cryptic. And I finally came up with a naming convention I'm happy with that I think will make things clearer to understand. And lastly, over here we called My Universe, My Viewport Monitors, Refresh All. This would refresh all the viewers after you made an update to the universe so that the user can see it in the viewport screen. This was a My Universe thing, so I changed that also to a function call that now makes sure there is a universe and that the universe has a viewport manager before then going and calling that, because that could throw an event that might make things miserable. So I think I've cleaned everything up a little bit better than it was before. The other improvement I made was in the coordinate representation in the center of the universe. I put a grid plane on top of the coordinate axes to kind of give you a scale reference. And unfortunately, what was going on is the center line of that grid was being drawn in the same place as the coordinate axes. So depending on your view angle, the display may show you the axis or it may show you the grid line. And that's kind of confusing. So what I did is I updated the grid line, the grid system, not to print the center lines. Therefore, when you see the coordinate axis now from any angle, you'll be able to see all the coordinate axes go through it. That was the other thing that was been bothering me for a long time. Okay, so now this is the coordinate system of the universe object. Now, unfortunately, a lot of my lingo, I call it the global coordinate system. It's the same thing. So if I say the universal coordinate system or the global coordinate system, it's the same thing. I should have picked one word, but unfortunately both words got mixed together. Essentially, the global coordinates or the universal coordinates are the coordinates where the ether is. Because in the end, when we do all of our objects in there, in the end, we have to compute their final properties, whether it be acceleration, velocity, Coriolis. All of those have to be computed with respect to the global coordinate system so that they're properly represented with respect to the medium. Okay, that's what the importance of the global coordinate system. In Physics 2, the medium is stationary. Okay, now every object has three kinds of parameters. You have construction parameters, which are typically the parameters that say, here's the size of my magnet, here's the current in my magnet, here's how many magnets there might be, yada, yada, yada. Okay, then what you do, once you specify your construction parameters, you call the onConstruction change, which will then take these and build all of your graphic objects and build all of your physical objects. And it may even update the local parameters. Local parameters are your local coordinate system. Relax if you don't understand it. We'll cover what that means in a minute. Okay, after you've done that, then you can update, if you need to, any of your local parameters, and then call on local change. That translates all the local coordinates into the global coordinates. Once you have the global coordinates, you can take measurements, and you can actually display the graphic objects that are created. Now, there's another little function that is called automatically for you at the very end of your onLocal coordinate change here. Once the global parameters are created, at the end of that, this guy will automatically call update the drawing for global change, which will update all the graphic objects, so then you can go right in and hit the refresh viewer without having to do this step here. Okay, so you've got pretty much three steps. You put in your construction parameters, and then you go on construction change, on local change, and then you can go right to viewing, which is what we're going to do in this video, because the update the drawings will be done automatically for you, so you don't have to deal with this step. It's done for you. But when you take a measurement, and we're going to talk about measuring in next week's video, this is when you can take your measurements after this guy has been done, because all your measurements, again, are relative to the global parameters, and those need to be properly expressed before you can take a measurement. There's no check here, so if you fail to update your global parameters and you take a measurement, you're going to get gibberish. Okay, so that's the three kinds of parameters: the construction, the local, and the global. Now, what we do is we represent all of our local parameters with lowercase letters, all lowercase letters. We represent our global parameters with all uppercase letters. Our construction parameters are usually mixed. Okay, and you can see here, this is the simple magnet thing that we did last time. And you can see the construction parameters. Here we want to display the edge currents. Here's the current in the magnet. Here's the diameter of the magnet. Here's the height of the magnet, the thickness of the magnet. Then after we're done, we add the object to the universe, and then we call on construction change, on local change, refresh viewers. Just as you see it there, except that refresh viewers is down there. Okay, so that should be pretty straightforward. Now, again, I'm going to repeat. Construction parameters are the general parameters for the setup of the object. For example, it could be the edge current. Am I going to draw the edge currents? What's the diameter of the magnet? How many segments in the circle? This is important. We're going to discuss this in a moment. Okay, and you can see those right here as provided by the F2 magnetic disk, number of segments in the circle. And here you can see what happens when you call on construction change. It gets rid of all the graphic objects. It clears the present frame, because this is developed from a frame. It doesn't clear the universe. It just clears the objects in the frame, because it's going to rebuild the magnet and append a circular wire construct. We'll talk about more of that in the next video. In this diagram, I'm going to demonstrate the importance of the number of segments in a circle. Let me show you something else I forgot to mention previously. This is the thing in the brackets is the default value. So if you do not override I, you're going to get 1000 amps. And do draw the edge currents. It defaults to false. In this particular display, I've got that set to true so that the edge currents are shown, and it shows it in this yucky purple metallic wire. So it doesn't get confused. I used to draw it in copper, but decided that I'm going to do it with the yucky purple so it doesn't get confused with a copper wire that might actually be put there for other reasons. Okay, so the diameter, when the magnet goes in, the diameter is in the XY plane in the face coordinates. And right now it defaults to, I think that's 1 inch. The height, which is in the face coordinate of the Z, and I'm going to explain what the face coordinates are in a minute, is 0.08 meters. Okay, now the number of segments in a circle, which defaults to 144, represents how many segments are in the wire representing the edge current. And you can see there's a lot more segments here. If you look at the actual circle that's printed, it's very, let me show a blow up of that. Okay, you can actually see, I think we only do 36 segments in a circle for the actual disk that represents the magnet, because it doesn't have any real effect, so having it that high resolution is a waste of time. But you can increase that. There's a way to increase that if you don't like the number of segments I'm using to represent a circle. Okay, but this guy it has such a fine number of segments in it that it looks like a nice tubular thing without segments in it. But there is segments. I can show you a blow-up of this. Okay, and if you look very closely, I don't know if you can see it, but there's the tiny little segments for each of the little filaments that make up the edge current. They're there. They're visible. If you look at them in the right angle and the right light, you can actually see them. They're made small enough so they don't have an effect on the precision, because they're actually small enough to not have an effect on the precision. Okay. So now let's talk about the local and global coordinates. There are two structures. I use a little v that represents this as a value type, which means it's a structure. You have PVA, which stands for position, velocity, acceleration. It's 3 vectors, 1 vector for position, 1 vector for velocity, 1 vector for acceleration. We have one of these structures at the local level, and therefore it's all lowercase letters. And we have another one that represents the global position, velocity, and acceleration. Okay, and I'll explain what the difference between local and global is in a minute. Then we have another 3-vector structure called X, Y, and Z. These are the face coordinates. This is the orientation of the object, which way its face is pointing, which way it's looking. That's why you can use the word face. Okay, and we have local face coordinates and global face coordinates. And again, I'm going to show you a picture of these in a minute. Okay, and this comment was not finished. So again, the PVA is a structure that contains a vector for position, velocity, and acceleration. Okay, now let me give you a PVA example right now. In this section, we're going to demonstrate what the PVA is. Okay, and what we're going to do is we're going to create a new thing for PVA. I'm going to call it play, because we're going to do something a little bit different this time. Okay, so we're going to copy this stuff from before. We're going to copy the clear all. Okay, to clear the universe, and then we're going to copy this stuff at the bottom to update the parameters and refresh the viewer. So what I'm trying to do now, instead of having to, stop and restart the software every time I want to make a little change to demonstrate, what I'm going to do instead is keep everything live. And I'm going to put this in a loop. Now, I could have put a while true loop here, but then if somebody inadvertently clicks on this menu item, the software will hang. So what I'm going to do is I'm going to put this in a limited loop for, pick a letter, W equals 0, while W is less than 100. If what I'm trying to demonstrate can't be done in 100 rounds of this, then 100 should be more than enough for what I need to demonstrate. I wanted a W. I hate when it tries to help me like that. Okay, so we're going to put this in a loop so that every time around I don't have to keep restarting the software. Okay, and I'm going to have a breakpoint. We're going to put, I need to put something here for a breakpoint. I'm going to put W equals W plus 0. This is just some stupid thing to breakpoint on. So I put a breakpoint over here. So let me just make sure this shows up first before we do anything else. See how long it takes to build every freaking time. So we're going to open up a viewer. I think I'm going to use F2 for location. And then we're going to run our example for PVA play. Okay, and let me minimize this window. So let's just, okay, I wanted to bring this guy to the front. Hold on. Let's let it run out. All right. Do it again, Sam. Get this guy out of the way. Open the viewer. Put this guy over here so we can watch. And then set up our breakpoint. And then I'm going to say, call the example guy here and say go. Okay, so now we can see the viewer and we can update the code. Come on, little kitty. I don't want to cuddle right now. You can go over there, get some sunlight. So what I want to do now in here, because now we're breakpointed, we can change the code, is I want to create an F2 charge. I'm going to call it Q. Okay. And right now I'm going to add it to the universe. Kitty cat, not now. She wants to cuddle so bad, and I got work to do. Sorry, baby girl. So much work to do, and all I want to do is cuddle. Okay, so I'm going to run this again to show that come up. And where is... Oh, F2. Oh. Sorry, I forgot to set the position this time around. Damn. Playing it again. Playing it again. Viewer. Move the viewer over there. Set F2 to get it to a location where we can see something. Then run the damn example. Let's make sure I got it right this time. Okay, and so there's our sphere. So now, anytime before I hit construction or local change, I can say my Q dot lowercase pva, because lowercase pva is in the local coordinates. And since I'm adding it to the universe, the local coordinates are in universal coordinates, or global coordinates. When I say universal or global, I'm meaning the same thing. So if I say q.pva.position .y, y equals, let's see, I want to move it up 3 centimeters in y. Then I set the y position to 3 centimeters. And let's see if this works now. Now I have to hit F5 and it should work. See, that's what I wanted to do. I didn't want to have to keep restarting it every time. Okay, if I want to move it up in Z, I can say q.pva.pose.z is equal to, let's move it up 1 centimeter in Z. And oops, hit F5, and now it moved up in 1 centimeter in Z. Okay, so that's the PVA. It's the position, velocity, and acceleration. Now I can set the position, velocity in a simpler method. Instead of sending them individually, I can say q.pva.pose is equal to new and vector, and then I can put 1, 2, 3 for my x, y, and z. Instead of doing this, it's always good to spell things right, and hit F5, and oh, I put it in meters. I apologize. So it flew off. That's 1 centimeter. 2 centimeter. 3 centimeter, F5 again. So that's how you can set the position. And again, because we're adding it to the universe, the position is relative to the universe. So this lowercase local coordinates means these are in the coordinates of the system you're adding it to. And then when you hit on local change, this gets transferred into the global coordinate, which would be the capital PVA. And right now, since we're already in the universal or the global coordinate system, then all it really does then is just copy this into the capital. This system of going from the lowercase to the capital is more important when we add this to a frame. So let's go add a frame to the universe. I have a new kind of frame, F2 frame special. I'm just going to call this S for special. Okay, and I'm going to add the special frame to the universe. And my universe.add special frame. And let's just hit the F5. Okay, there's our special frame. Now what I want to do now is show you the difference between this. So now this frame has its own coordinate system. Right now when it's created at the origin by default with its x-axis aligned with the global x-axis, its y-axis aligned with the global y-axis. Oh, and I changed this from the last video. I had red, green, blue, but I decided since I made my y-axis yellow that I should make the second square yellow. So the boundary between, so red, the right side of the red is the x-axis, the right side of the yellow is the y-axis, and blue is normal. That is normal to the face of this new coordinate system. So now if I move this object, okay, let's just reuse these guys because the frame also has a PVA. And we'll just change that to S instead of Q. And then we will run this. See, now I moved this frame over in X and up in 1. But you notice the blue ball didn't move. The blue ball stayed the same. Okay, and the reason why is that both of these are moving within the framework of the global frame. Now this global universe is also a frame. Okay, this is a framework inside of a framework. Now what we're going to do is we're going to add the ball to this front. First we're going to put the framework back to 0, 0. Okay, and now instead of adding the charge to the global universe, we're going to say s.add s.add q. So instead of adding it to the universe up here, I'm just going to add it to this local framework. Now, because the local framework is still in the location of the global coordinate system, you're not going to see the ball move. So let's just run that to verify that. Okay, everything stayed in the same place. Now what we're going to do is we are now going to move the local frame, the frame special frame. And because now the ball is in the coordinate system of the special frame, now when I move the special frame, the ball will move with the special frame. So now let's run that. Okay, so you can see they move together. Now, let me show you something. Now, what you can do here is you can now say to the special frame, it's got its omega variable is equal to radians from degrees. So I'm going to rotate it 45 degrees. Now these rotations are always in the z-axis of the reference frame. Always in the z-axis. So when I rotate this 45 degrees, everything, including the ball, because the ball is in this guy's reference frame, 45 degrees, F5. I'm sorry. Omega is the velocity. Theta is the, got the wrong one. Theta is the angular position, omega is the angular velocity, and alpha is the angular acceleration. Sorry. Okay, so that all moved 45 degrees. Okay, so this ball stayed within that reference frame. So now in this reference frame here, the x-axis is now 45 degrees relative to the global coordinate system. Its y-axis is also 45 degrees offset from the global. But because these guys rotate in the z-axis is still parallel to the global coordinate or universal coordinate frame. Okay, and that is the beauty of these, because you can put rotations inside of rotations inside of rotations. Now the other thing you can do is you can tell this reference frame not just to rotate. Let me actually put it back to 0. And I'm now going to rotate it using the face coordinates. Okay, so now we're going to discuss what the face coordinates are. The face coordinates is the direction of the x, the y, and the z. You can offset that with the theta parameter like I did here. You can also offset it with the face coordinates too. So what I'm going to do is put s dot face, lowercase face. And what I want now is I want the x coordinate of this guy to be aligned to the z coordinate. And so I'm going to sit here and say face, and I want your x coordinate. Now again, what I'm putting in here is the coordinates of his x-axis relative to the coordinates of the global reference frame, or rather the reference frame he's inside of. Because if you put a frame inside of a frame, then these local coordinates are the parent of the frame. In this case, the parent is the global coordinate system. So let's make x line up with the z. So we want to say x is equal to vector 3, 0, 0, 1. So we might make the x and the z. So if we do the x and the z, now you have to do all of the coordinates if you're going to move one, and they have to be orthogonal. They have to be proper. I don't have time to give people a course in that right now. Okay, so if x is going up, let's make z go along y. Okay, that means that if x is going up and z is going along y, that means x is going to go along, wait a minute, see, x is going on, that means y is still going to be going along y, so that should be fine. I believe no, y is going to be going along. Oh, I'm sorry. I got my coordinate system messed up here. So that means that z, yeah, this is why this part is confusing. And I'll show you a simpler way to do all this. I'm pretty sure I got that right. Let's find out. Okay, so there we go. The x coordinate is going along y. The z coordinate is going along minus x coordinate. And the, let's see, x is along z. Yeah, there it is. X is along z, y is still along y, and the z is along minus x. And you see the ball moved with it as well. Okay, so you can do this. You can actually set the face coordinates. This is, this is the coordinates of this reference frame in the coordinates of its parent frame. Okay, and once you do that, any object in this subframe is going to move with it. And we can still even rotate it after that. This rotation is applied after the face coordinate. And so that will rotate at 45 degrees. Okay, so you can do all these compound rotations, make life easy, make life more complicated, however you want to do. Now, let me take off this rotation for a second. Okay, so if you don't want to move it this way, have another way, which is using a simple utility. And you do V face. Oh, VXY. So the type is VXYZ. That's what the coordinate. That's what the face coordinates are. They're an instance of VXYZ. And then you can say over here, Z faces toward minus X. That'll pretty much do exactly what we just did. Or if you want to rotate it, let's rotate it around. Let's rotate it around the X-axis. No, let's rotate it around the Y-axis. Okay, and let's rotate it by 30 degrees. These are in degrees here. Okay, so that'll do, if you want to do partial rotation. So now we basically took the Z-axis and rotated it toward the positive X-axis by 30 degrees. And of course, you notice the ball moved with it because the ball is in that coordinate system. Okay, so that ends this section on simple face motion. So I've explained here what the position, velocity, and acceleration are. Now, for drawing purposes, we only use the position. But in computation for all of the electromagnetic effects, the acceleration and velocity are used there. So you still have to set those if you have a charge that's accelerating or whatnot. Now this system, when you do on the local change, it's going to compute all of the Coriolis, and that'll be included in all of the accelerations. Like for example, are we rotating here? Okay, so let's do this. Let's go look at our ball after. We have to look at it after on local change. So we're going to break point, and we can do it right now. We can go to Q. Okay, so PVA is where we put it initially because that's in the coordinates of the special frame that it's in. But now if we look at the PVA here, now this is the position in the coordinate system, in the global coordinate system. So you notice that that's different from this, which has simple parameters that we put in before. So I'll say that one more time again. Okay, PVA, the lowercase PVA, is your position, velocity, and acceleration in the frame that you're in. The capital is adjusted for the global or universal coordinate system. Because your global or universal coordinate system is the coordinate system of the ether. And so all moving particles have to compute their electromagnetic effects on their velocity relative to the medium, or acceleration relative to the medium, or even the position among each other if you're going after Coulomb forces. So that's why we always have to resolve everything to the global coordinate system, the capital parameters, the global parameters, so that we can compute the electromagnetic effects. Okay, I'd like to mention the difference, what's special about a special frame. Okay, if I just put in a normal frame in here and run this, you'll notice you can't see where the frame is because the normal frame is invisible. Okay, the universe is made from a frame as well, and that's why I added this coordinate system with the grid to the universal frame so I could see where the origin is and am I placing my objects correctly relative to the origin. Okay, but when I developed the idea of putting a frame inside of a frame inside of a frame, I got this where you have to sit there and really see where the object inside the other frame is, and it became a pain. So I made the special frame so that you could see the orientation of the special frame and if you got all your rotations correct. And that is why I developed a special frame, which makes that fancy color wheel. Now this page here represents one of our spec sheets. We have a spec sheet for each object you can place in the universe. And we're doing this one here because that's one of the ones we used in the demonstration. Now, for those who don't understand class inheritance, what it is the F2 magnet inherits properties from a generic F2 magnet class, which is abstract. F2 magnet is built upon the F2 wire. F2 wire is based upon F2 frame, and F2 frame is derived from the basic object abstract class here. Okay, you'll notice that this has purple text, and as you can see, this is the stuff that F2 magnet disk inherits. The local and the global PVA are supplied by the F2 object, because every object that we're going to have is going to have a position, velocity, and acceleration, a global one and a local one. Okay, the frame that we demonstrated before, that's the one that cares about which way its face is oriented. That's where the term face comes from. Okay, and that's why this guy, the frame, provides the face, both local and global coordinates, as well as the angular offsets. And we have a demonstration of these in a moment. F2 magnet, it actually is a part that supplies the ability to draw or not to draw the edge currents, and also sets up the F2 wire for representation as an edge current. Okay, F2 wire also gives the edge current. So that's the part that you supply when you say, I want to set the edge current. That's where the control comes from. Even though you're doing it through magnetic disk, the control actually comes from this. It is inherited by this guy. Okay, and the F2 magnetic disk, because this text is black, he supplies the diameter. And what this means here is that the diameter is in the local face coordinates in the XY plane, just like you see it there. Height is along Z. These are the default values inside the brackets. So if you do nothing, if you do not do anything, you just place one in the universe, it's going to have a default edge current of 1,000. This is green because this is defaulted by the F2 magnet. The normal F2 wire defaults everything to 0. So to make sure there is some edge current in there, so you don't put a magnet that has 0 current in it by accident because you forgot to set the edge current, I just defaulted to 1,000 for you. That's done here. But you can override it to any edge current you like. The draw edge current is we'll draw that. We'll show you that sickly purple wire that comes around at the boundary between the red and the green in a moment. The diameter defaults to 1 inch. The height defaults to 0.08 millimeters, a little bit bigger than a 1/16 of an inch, I believe. I don't remember what that one is. And the number of segments in a circle. We're going to explain what all this means in a moment. Okay, and you do have access to the complete wire factory controls, so you can actually add stuff. But the problem is every time this disk magnet gets redrawn, it's going to wipe out anything you add to the. So don't use the wire factory controls, because on construction change will override all except the following. So you can set the current change, the Q, whether you want impulses inserted or not. It's false for the magnet. What type of material you want to use to represent the magnet edge current with. I don't recommend you overriding that. And what kind of wire diameter do you want for display. Okay, and you can see that here. Here's F2 magnet disk is derived from F2 magnet. Here's F2 magnet derived from F2 wire. And I could take you all the way back to F2 object. Here you can see the do draw edge current is supplied by the F2 magnet. And here's the constructor for F2 magnet, which sets the edge current material, turns off the insert impulses because we do not want centripetal or Venturi forces being emitted by the wires that represent our edge current. And here's where we default the current. Here's where we default all the other items. I'm going to talk about number of segments in a circle in a second. Now let's talk about the face coordinates. Okay, the face coordinates are built on an XYZ, a trivector. All of trivector is, it's got an X and a Y and a Z. Okay, and the default for these are the global coordinates, where the X direction goes off in the X direction, the Y direction goes off in the Y direction, and the Z direction goes off in the Z direction. Literally, you can have the local coordinate system of your frame pointing in any direction you like, different from the global. This is the default for the global here. Okay, now let's talk about rotating translating reference frame. Okay, so when you get on this roundup, okay, and you walk in, this thing is sitting on the ground, and you pick a chair, a seat. Okay, you're always then going to be in that seat, regardless of how this thing spins or lifts in the air. So within the reference frame of this ride, you're in the same location relative to the ride at all times. So, but when the ride starts spinning, now you're moving relative to the outside, to the global coordinates, and then when it lifts up in the air, again, you're moving in differently to the global coordinates. But relative to the coordinate system of this thing, you're still in the same chair. Okay, so that would be the local coordinate system of this guy, and your coordinates, your local coordinates, are relative to the coordinates of this wheel. But your global coordinates are moving around in a circle up at a slanted circle. So there's a difference between your local coordinates and your global coordinates. And this is how we are able to put rotating reference frames inside a rotating reference frame to compute very complicated magnetic interactions. So the basic frame that we use is called the F2 frame. Here's your global coordinate system, that thing that would have the grid spacing on it. I should use yellow here. But I'm using green because yellow is hard to see against the white background. Okay, so when you put in a frame, you're going to give a position, velocity, and acceleration of that frame relative to the origin of the global thing. And these coordinates are in the reference frame of this guy, of the coordinate system of this guy. That's why the lowercase. These are the local coordinates in the encompassing frame. Okay, and your face coordinates are the vector that defines in what direction your face of your wheel is. Okay, next, so what you can do is you can offset your face by changing that face coordinate. So it's just saying that, well, now I want my z to go off at 45 degrees, and that'll rotate up your x, yada, yada, yada. So your face coordinates can give you a different orientation at the point where your origin is, which is defined by your PVA. And these are all lowercase, which means they're the local coordinates. Okay, you also have in your local coordinates your theta, which is your angular displacement, your omega, which is your angular velocity, and your alpha, which is your angular acceleration. Okay, these of the variables, omega, alpha, velocity, and acceleration, are not seen in the graphic. They are used at the computation level. So if your things do have accelerations, those will be included in the computations for your electromagnetism, but they are not something we can draw. But anyway, so your theta will give you an angular offset, and so your rotation of your wheel where you're sitting is now going to be in a different location as the theta variable increases. Okay, that when you call on local change, the computer is going to take your face, your PVA, your theta, your omega, and your alpha, and compute your global location and your global face coordinates. Now, all of your parameters are relative to the global reference frame, and now we can take a measurement of your charges relative to the ether. So let me give you a demonstration of that. If it wasn't clear, I don't know, I might just end up making it more unclear than it was before. I don't know. It's hard to explain. This stuff is hard to explain. It really is. In this section, I'm going to show a little bit better of an example of how frames work. And so we're going to make a new example called frame compound. I wish I could spell. So what we're going to do the same thing. We're going to do the clear all at the beginning. And then we're going to do these three at the bottom. Okay, then we're going to make a special frame. And we're going to add it to the universe. Matter of fact, let's call this S1 because we're going to make 4 frames. Okay, and then what we're going to do to this frame is we're going to add an inert post, an inert cylinder to kind of give it a central post. I already made one from before, that's why I have this. Okay. And I want to move it up. I have to move that up in Z. Oh, let's do this one instead. And then we can do edit, advanced, uncomment selection. Okay, and then we want to say S1 add. Okay, so we want to take a look at what we just did. We're going to start this. I'm going to go view, hit F2 to get in a nice location, and then run the example for frame compound. Okay, so what we have is our post. I got to select this. That's, I'm going to hit that. I'm going to set that as position F4, Shift F4. So what we're going to do now is we're going to add 3 more of these. Oh, wait, before I do that, I want to rotate this by 22.5 degrees. So we're going to rotate the frame. We're going to change the face coordinates. S1 dot face is equal to VXYZ dot. We're going to create an XYZ frame from a rotation around the Y-axis, and we're going to do 22.5 degrees. Let's see what that looks like. See what that looks like. Okay, F5, oh, we got it there. View, and then we hit F3 to get to our location, and we run the frame. Okay, so there it is. It's rotated 22.5 degrees. Okay, now we're going to add 3 more of these rotated at 22.5 degrees. Now, I could sit there and type these all in over and over again and make S1, S2, S3, S4, but that's a lot of work. But you can do that. But the other thing you can do is you can also clone. So I'm going to say frame special dot S2 is equal to S1 dot clone. Okay, that's going to make a complete clone of the frame, but since it returns as a standard object, we have to say as frame2 special. Okay, let's make a couple more clones. There's 3, and there's finally 4. Okay, now they're not added to the universe. If I add them all to the universe right now, they're just going to be painted white on top of the other. You're only going to see one. So what we're going to do is we are going to add S2 to S1. So we're going to put a frame, a rotating reference frame, inside a frame. S2. Okay. And then we want S2. Let's see what that looks like. F3. And then we run the example for... Okay, so because each one of them are assigned to the origin, let's rotate around here. look right along the z-axis here. Okay, so our first frame is rotated 22.5 degrees, and we put the second frame in him, so now he's rotated 22.5 degrees relative to this guy. And this guy is rotated 22.5 degrees relative to this guy, and this guy is rotated 22.5 degrees relative to this guy. And you can see his final frame Z is now oriented in the X direction. And we can go look at that, and let's do that right now. And where the place you need to look at it is after you do the on-local change, because that's what does the final coordinate. And we'll put the breakpoint right on refresh viewer, because the coordinates should be updated after this. So we're going to go back to example, frame compound, and now we're going to look at S4. Okay, and if we look at his final face, you see that his Z the 1 is right along the X coordinate axis. So that means his local coordinate system, the global direction of his local Z, okay, is along the global Z's axis. Y is still along the Y axis. And in this case here, we can see that his X coordinate of his local Z frame is along the global minus X. And we can go look at that here. Oh, we got to run this so we can look at it. Okay, because there, between the green and the red, that is his X coordinate, which is along the minus Z axis. Okay, let's do something else. Let's stack these guys one on top of the other. Let's do that. Okay, these posts up here are 3 inches high each. So all we have to do each one of these here is we're just going to say S1 dot, oh no, S1 we want to stay at 0. S2 dot position PXYZ PVA, his local PVA, and we want to move it up in Z 3 inches. Okay, and then we're going to say PVA dot X, no, Z, and we're just going to use this height guy here. Position Z. There we go. Now, what I could do, instead of typing this in 3 times, I could say S2, S3, S4, because this is all I'd have to do. Let's just show you what I mean instead of 3, F4. So we're moving them up in Z in their local coordinate system. F5 will run. And then we're going to do let's show it first. F2. Oh no, we're doing F3 this time. Example. Okay, let me move back. See if there's a better location I have in there. No, I don't. Okay. There we go. Okay, so you see how they're stacked, and this guy here should still be, even though this looks like it's not parallel to the x-axis, that's kind of just a deformation of the viewer. Let me go down a bit. That should be, look at it from a better angle. There we go. It's kind of a fisheye view this viewer has. Okay, so now we can go look at his Z coordinate again. Okay, now we're going to look at his S4 again. Okay, that's the final object. If we look at his local PVA, where is his local PVA? Okay, again, he's only moved up 3 inches in Z. So relative to the coordinate frame he's in, he's only moved up 3 inches in Z, which is 7.62 centimeters. Okay, and then so his face. Okay, but because he's compounded, his actual PAV and global coordinates, he's moved up all of that amount right there. So that's where the center of that final frame is. He's up there. Now look at his face. His original face, lowercase face, says he's only rotated by 30 degrees. That's what that means. But if we look at his final global face coordinates, that shows that again that the z-axis is pointed along the x-axis of the global coordinate system, and his x-axis is pointed along the minus x direction. The minus z direction of the global coordinate system, and his y direction has stayed the same because remember we rotated this along the y. Okay, now instead of me having to update all of these, what I could have done here instead is just updated one of them. After I cloned it, and then cloned that one for the final two. So the judicious use of clone will save you having to do a lot of unnecessary work. And if we do this, we'll show you that that works the same. View, F3. Oh, I should have saved that other location. Yeah. Remember to select the frame before the keys work. Okay, you can see it's all as it was before. Now let me show you something fun here. Now one feature that these special frames have that I haven't shown you yet is they have the ability to auto-rotate. So what we're going to do here is we're going to set the first frame, so we don't have to copy it to all the others. We're going to set the first frame to rotate auto rotate mode equal omega. What that means is the omega variable is going to be continually added to the theta. The omega is the angular velocity, and we're going to be updating the angular offset, the theta variable, with the omega variable. So we want to make sure that we set that omega to, let's see, radians dot from what? There should be a turns per second option. What the heck is going on with this thing? Oh, it should be radians per second. That's what I want. From turns per second or rounds per second. I have both of them in there because I can never remember which one it is. And so we're going to do, I want it to run slowly so you can watch it. So I'm going to do maybe 0.25, no, 0.1 turns per second. Make it slow. Okay, now I'm going to show you, this isn't going to run because I need to emphasize something you need to do to make this work. So when we run it, and view it, okay, nothing's working. Because what you need to do to enable animation at the very bottom, and this is in the notes, you have to say form 1. I think I have a... just say form 1.timer 1.enabled equal true. I should make a special simple command for this. This is form 1. Oh, it's capital F. Form 1, timer 1. All right, which is it? Timer 1. All right, I just should be able to go timer 1. I don't know why. Equal true. Why that was giving me problems, I got to go find out. Okay. Take the view, F3, then pull out a little bit, and then do the example. Okay. Oops, let me make this big screen here. Kind of hypnotic, isn't it? So this is what I mean. You can have a rotating reference frame inside a rotating reference frame inside of a rotating reference frame. And then once you get done setting this up, and you don't need the little color wheels to see where, in fact, your frame is and how it's behaving, okay, then all you have to do is just say, go to your first frame and say S1 dot enable equal false. I believe I fixed this, so this should work. F3 and then pull out. You should still see the center posts if I did this right. There we go. All right, well that's the demonstration. It gives you a good idea of interplay between frames, what the difference between the PVA and the frame is, and the difference between the local and the global versions of those variables. Okay, so that ends this little demonstration. Okay, now that we're back from that demonstration, let me give you a quick overview of the available objects. Okay, this is your disk magnet. We've already discussed this one in great detail. And again, I forgot to mention in the previous one that your edge current is right-hand rule. North side up is green. So if your magnet is situated at the global coordinates, and you put a positive current, that'll put your north side to Z, and your current goes in the right-hand rule where your thumb is along Z. Now, disclaimer, Physics 2 uses positive current flow model, also known as whole flow, or some people say engineering flow. The only place where this gives an incorrect answer in Physics 2 is when computing centripetal charge motion. As shown later how this is compensated for. Not in this video, and in the next video when we take the measurements, I'll show you how we compensate for the centripetal. Okay, we have rectangular magnets. Now, do not use for rotating experiments, and I'll explain why. When we create this magnet, we create one long segment for each side of the magnet, one segment. You remember the disk magnet where we had 144 segments to make up the circle. Since that's already segmentized, that'll work fine with rotating experiments. I need to put a control in here that lets you specify the segmentation of this wire. Here's the reason why. This wire is segmented. When the software computes the effect of one wire filament against another, it'll automatically chop it up. The problem, what it can't do, is compute the individual Coriolis effect for each one of those little automatically chopped up segments. So what happens is when you hit the local parameter change, the Coriolis effect for this entire wire that would be here is computed at the center of the wire, and that's used for the entire segment. So even though we're chopping it up internally to do the computations, we don't have the means to go out and recompute the Coriolis effect for each one of the little automatically chopped up segments. So what you have to do is chop this wire segment up yourself to enough segments where the error in the Coriolis effect go to 0 if you're doing a rotating experiment. Okay, I'm going to be adding a control to this which says use segmentation and what the differential length of segmentation you would like is. So that has to be added to that before you can use a rectangular magnet for rotating experiments. Charges, pretty straightforward. If your charge defaults to 0, you get this bluey, purplishy, glowy thing. If your charge is positive, you get red. If your charge is negative, you get a black sphere. Pretty simple. Frame, well, your normal frame does not draw anything, so I don't have a picture for this. But essentially, as stated before, your frame object is derived from F2 object. The F2 object gives us the PVAs. The frame gives us the XYZ, the theta, the omega, the alpha. And the F2 object all gives us the do draw. Okay, if you set that to false, it prevents all the enclosed objects in that frame from displaying or drawing. So be careful when you're using do draw and setting it to true or false. There's also methods for this where you can add an object to this frame. It's the same method you're calling when you add an object to the universe, because the universe, the F2 universe, is also derived from F2 frame. When you clear, same thing, it clears all the objects in the frame. Clone allows you to return a copy. I think I've demonstrated that to you in the previous. All objects should inherit clone. I believe clone is provided from F2 object. There's a special clone frame where you can clone the frame without cloning the objects if you so desire. That's there as well. Then we have the frame special, which is a new object added within the past couple of weeks, so I can demonstrate how frames move and work. I've demonstrated the auto rotation, frame reference wheel, enable the frame reference wheel. Now I've also added another thing where you could actually set the colors of the sectors. This is section 1, 2, 3, and 4, and you can actually change those. I haven't shown those here yet. So if you wanted to highlight a particular frame by, let's say, using gray and black or black and white or some other color scheme so you can determine one frame from the other, that's the possibility you can do now. Now again, auto rotation requires you at the end to make sure you set timer 1 enabled so that the auto rotation will occur. Okay, we also have an inert cylinder. The normal material is copper. I'm showing it set to gold. But basically this cylinder is inert. There's no charge. It doesn't affect. It's there so you can put something in there if you need some kind of reference. You saw I used it in the example as a Z reference, a 3-inch Z reference for the reference frame, so that I can have a post that represents Z for each of the reference frames. There's also an inert sphere. Its normal default color is silver. In this example, I am setting it to blue metal for this little picture here. Again, it has nothing much more than the number of segments in the circle is how it chops up, how precise you want the sphere to be. If you're going to have lots of these, I recommend you reduce this to maybe, I don't know, to 18 or something like that. Unless you want a perfect circle, then increase that number. That's the default value right there. Okay, filament. This is your basic wire construct. Again, you need to segment this if you're going to do a rotating reference frame. But I really recommend you that you don't use that. You can. I do use this from time to time. But you're better off using the wire thing. This guy is basically a collection of filaments that are connected together. So you can see the little cuts in here. That's because each one of these is a little filament object linked together to make this, very convoluted inductor, resistor, whatever you want to call that. Now, there's a lot more parameters and a lot more controls. This object is very, very complicated. We're going to save this one for the next video where we can look at it by itself, because this is the bread and butter of physics 2. Okay, then we have a simple circular loop. This is what we use for the edge currents of the circular magnets, or if you just need a simple loop. This is the rectangular loop. Again, we don't have the segmentation for this, so don't use one of these on a rotating experiment unless I put the controls in for segmenting it right now. Same thing. The centripetal value is computed at the center of each segment. This guy here. So the centripetal value for each segment is computed at the center and used for the entire segment. That is the reason for all these red blotches and all of these things. This one has controls for segmentation. And again, next week I'm going to show that to you. This one's already segmented by the number of segments in a circle. Again, you need to have segmentation for this in order to use it for rotating experiments. We should have that fixed before the software release. This is the force rose. I don't know if I've implemented it. No, I don't know if I'm going to implement it for physics 2. Because we have the indicator plane, which is a lot more, it gives a lot more information. We'll see. Maybe I'll add the physics rows to be compatible with older experiments. Now again, this guy here, he's very complicated, had lots of controls, and we're going to demonstrate this in the next video, because part of the next video is showing you how to pull out the data and put it into a file. And this guy, you can pull all his data out. We're going to talk about this guy next week, because I can see you all getting glossy-eyed and overwhelmed. So we're going to cut this video short. So what I did is just remind you what I did. I did an overview of the coordinate systems, what the difference between a PVA and a face is, what global and local is. For most people with STEM training, this should be more of a review. The little bit of difference you might never seen before is the global and local coordinate systems, at least not represented that way. For others, let me know in the comments what confused you, and we'll see about scheduling more help videos to help shore up those areas that you weren't sure about. Now, the tech sheets that I show with the object details will be published in a separate PDF and be available with the software. In the next video, we're going to complete the discussion of the wire construct and the sensor plane. And then we're going to demonstrate how to make measurements using force, Vim, and show you the available interactions, and then finally show how to dump data to files for further analysis. Thank you, everyone. If you want access to this software right now, it's only available to engineers and above, Patreon engineers and above. I'm trying to get this site updated. I got the website updated. I'm having trouble uploading it to the server, but all of the new Electromagnetism V5 video series, and I also put up the Transvariance video series, which I forgot to put up the last time. I'm just trying to upload it. It's all done. The website's updated. I'm just having a problem uploading it. These idiots keep changing the tools. Every time I get used to knowing how to use the tools, they keep changing the tools. This is the EtherealMechanics blog site. Shout out to Sebastian for taking care of this. Again, when I get more time, I'll spend more time here. This is the YouTube site for EtherealMechanics, where when all these videos go public, this is the place they go. Thank you. No more voodoo physics.